All right, AP Chemistry. So in the last video, we ended up deducing that the Q of the lead is going to be equal to negative Q of the water. And we ended up setting up this equation. The mass of the lead times the specific heat capacity of lead times T final minus T initial of lead is equal to negative mass of H2O times the specific heat capacity of H2O times T final minus T initial of H2O. I'm going to go about trying to plug in these values and solving now. So my mass of lead given to me before was 2.85 grams. My specific heat capacity of lead was 0.128 joules per grams degree Celsius. T final minus T initial, which is 10.3 degrees Celsius. Then negative, my mass of water was 7.55 grams. My specific heat capacity of water was 4.18 joules per grams degree Celsius. Notice how I keep on putting all these units in. And then don't forget what specific heat capacity is. Specific heat capacity is the energy required to raise 1 gram of a substance by 1 degree Celsius. And then T final minus 52.3 degrees Celsius. And remember, T final is the same for both substances. They reach thermal equilibrium. So at thermal equilibrium, both objects reach the same final temperature. All right, so T final of lead is equal to T final of H2O. So if I want to start plugging and chugging, all I'm doing is solving for T final. So let me just start trying to make this look a little bit less massive. I'm going to do 2.85 times 1.28. Now I'm multiplying grams times grams, and I'm going to get joules per degree Celsius. I like to keep units in order, so you know that I didn't fudge up on the units. So 2.85 times 0.128, and I get 0.36, I'm going to just round to 3 sig figs, 0.365 joules per degree Celsius is what this is now. T final minus 10.3 degrees Celsius. Now I have my left side, right? I just combine these two, and I just have my left side, equals, I'll do the same thing to my right side, minus 7.55 times 4.18. And I'm going to get 31, I'm going to just do 3 sig figs, 31.6. Remember, grams cancels out. If I have grams on top and grams on the bottom, they cancel out. Joules per degree Celsius. T final minus 52.3 degrees Celsius. All right, and so I end up with a little bit less massive of an equation. And now I'm going to try and solve for T final. Okay? Now, there are so many different ways algebraically that you could solve for this. Some of you may just like move this to this side and move this to this side and do a bunch of fancy things. I like to just distribute, right? And then just solve for TF. So I'm going to distribute on this side and distribute on this side. So if I have like, this is kind of like seeing if I had like 5x minus 2, right? This is exactly, I mean, this is just in case you're like, Mr. T, I have no idea what you're doing. I just wanted to show you where you would see this in math class. You would see like 5x minus 2, and then you multiply 5x minus 10, right? So you distribute into the parentheses. So I'm going to show you that I'm going to distribute into the parentheses, and I'll get 0.365 TF, right? And of course, this is joules per degree Celsius. All right, that's the units. This is my variable now, TF, minus, because it's going to be 0.365 times 10.3, so 0.365 times 10.3, minus 3.76. Now this is joules per degree Celsius, and this is going to be multiplying times degree Celsius, so I will get joules left over here. They'll cancel out, don't worry. All right, so I'm just trying to keep track of my units. Then I'll do don't be careful. I have a minus sign here. There's a reason why we have the minus sign. If you don't have the minus sign here, you're going to get the wrong final temperature. So I'll do minus 31.6 times TF, and I get minus 31.6 TF with the units of joules per degree Celsius. And then I'm going to do minus 31.6 times minus 52.3 degrees Celsius. And remember, the degree Celsius will cancel out, okay? So if I do this, minus times minus is going to be equal to a plus. So negative, remember this minus, I distributed it over here. So negative 31.6 times negative 52.3. So negative 31.6 times negative 52.3. And I get positive, right? Because negative times negative is positive. Positive 1/6. I'm going to use 3 sig figs. So I mean, I am going to round, but I'll round this to 1,650, right? That's 3 sig figs, right? So I'm just going to round it to make it simpler. I'm going to write the number that I get from the calculator on top, so you're like, where'd you get that number from? In the calculator, I get 1652.68, but I'm going to do sig figs as 1650 joules, okay? Right? Degree Celsius cancels out with degree Celsius, and now I'm left with this as far as units, right? So I know I have a lot going on here, but I want to combine like terms now. So I want to have all the TFs on one side, and I want to have all the joules on another side, right? So that's another reason why I kept units in, so your units could cancel out nicely, and you know what unit you get in the end. So I'm going to just add 3.76 to the right side, and I'm going to add 31.6 TF to the right side. 31.6 TF to the right side. This cancels out. This cancels out. 0.365, and remember, this is joules per degree Celsius also. 0.365 plus 31.6. 0.365 plus 31.6. I get, rounding, I get 32.0. I'm going to, like on the calculator you get 31.965. So I'm going to round that to 32.0, right? TF, and that's joules per degree Celsius. And I get, on this side, I get 1,650 plus 3.76. 1,650 plus 3.76. I get 1,653.76, of course, which again, if I wanted to do 3 sig figs, again, I'll have it as 1,650, right? I'm going to keep this non-rounded answer so it's not the same as before. I'm going to make sure I have the correct number of significant figures in the end. I'm just switching it up so you see how it doesn't matter when or where you use significant figures as long as you express your answer to the correct number of significant figures. So I'm just going to make this 1,654 because that rounds to, the calculator gives me it as 1,653.76, and that's going to be 1,654, and these units are joules, okay? And now, how do I solve for TF? If I want to isolate TF, I divide both sides by 32. Divide both sides by 32, and the units that were associated with it were joules per degree Celsius. And so, if I do all of this correctly, if I divide both sides by 32, not only will I get the correct units of degree Celsius, I'll get the correct answer, 1654 divided by 32. I get, for 3 sig figs, I get 51.7 degrees Celsius. Okay? So, my final temperature for both objects is 51.7 degrees Celsius. 3 sig figs. And so it looks like the lead gained a lot more temperature, and the water only lost a little bit of temperature. However, you have to remember that they have vastly different heat capacities. The smaller the heat capacity, the greater your temperature can change. That's why metals tend to have very, very tiny heat capacities, because they could change temperature rapidly. The larger your heat capacity, the less temperature that you could change. You need more energy to change you. You need less energy to change you. And remember that for a future multiple choice question and short answer question, that the smaller the heat capacity, the more temperature you could change. It means it requires less energy to change your temperature. The larger the heat capacity, the more energy it requires to change your temperature. So it looks like our final answer is 51.7 degrees Celsius. Now, if you didn't like this mathematical way that I did it, you don't have to include units as long as you have the correct units in the end. So for example, if you wanted me to simplify and not have like all those freaking units, your thing would look like this. It would look like 2.85, 0.128, and then TF minus 10.3 equals negative 7.55, 4.18, and then TF minus 52.3, right? Some of you might give me this and then just solve for TF, right? So I'm just trying to show you, if you didn't like all my fancy units there, I'll just do it the same way. I'll do 2.85 times 0.128, and I get my, I'm not even going to do sig figs. I'll do my 0.3648 TF minus 10.3 equals 7.55 times 4.18, and I'll get negative 31.559 TF minus 52.3. I'm trying to do this like a quick way without all the fancy units, right? And if I distribute like I did before, I'll get 0.3648 TF minus 10.3 times 0.3648, and I get 3.76 equals negative 31.559 TF plus 31.559 times 52.3. I should get positive 1650.54, right, if I multiply these two together, right, without, and I get kind of like my same answer as I had before, right? And then if I want to solve for TF algebraically, I want to combine my TFs, so I'll add 31.559 TF, 31.559 TF, I'll add 3.76, add 3.76, I'll get 31.559 plus 0.3648, and I'll get 31.9238 TF equals 1650.54 plus 3.76. I'll get 1654.3, and then algebraically, to solve for TF, I would just divide both sides by 31.9238. 9238, right? I'm just doing this a quick way, how you may do it without units. A lot of you do this on tests, and I don't like this because sometimes you're like, what unit should I have? And some of you kind of depend on remembering what units your answer should be in, and that's weak. So make sure that you understand the units that involved in everything. And so if I solve for TF, I would get TF equals 1654.3 divided by 31.9238, and I get 51 point, if I want to do sig figs, I get 51.8 degrees Celsius, which is only 0.1 difference than our answer of 51.7. So obviously both those answers are beautifully correct, right? So this is the quick way to do it, where you just plug in numbers and solve for TF. This is linear algebra. So if you have an issue with linear algebra, please let me know. So we'll have to try and do this differently or show a different video doing just straight up linear algebra. But this is linear algebra where you solve for the one variable. Watch my previous video where we decided on how we got to that equation, where we set both Q's equal. And then in the end, when we solve for TF, we get our final temperature is 51.7 degrees Celsius, 0.7 degrees Celsius. You'll have a question similar to this on your test or quiz when you get back next week. So let me know if you have any questions or concerns. This is probably a really tough question to have to swallow in order to answer.